Okay, lesson 44. Some of you guys I know we're already reading. It's chain rule, it's alternate definition of the derivative, it's symmetric derivative. So again, we're in derivative world. It's all about derivatives. We will, I think it's towards the bottom and on the back, we talk about alternate definition to derivative. So that definition of derivative you already know. I mean, we kind of have two versions. We're going to talk about a third version. Now, before we do that, though, we're going to talk about chain rule. And I know we talked about chain rule, maybe last week, week before. And it's the same chain rule, but we're going to talk about a little bit different notation here. So as you look up top there, dy dx, so the derivative of f of g of x. So when you have a function inside of a function, is equal to f prime of g of x times g prime of x. So again, this is the derivative of the outside, keep the inside the same, right? Times the derivative of the inside. Now, I have another way I'm going to write this too. And this just kind of goes with the setup of today. I'm going to say or, the idea that dy dx is equal to dy du times du dx. And we're going to talk about this variation today. And I'll probably show a couple different ways we can think about this, at least on one of the examples to kind of relate them for you. But you'll notice as we talk about the chain rule today, these are set up a little bit differently. It's not set up as take the derivative of just one equation. They have it broken into two equations. So that's why I kind of want to talk about this. So example 1. Let y equal u squared plus 4u. And u is 5x to the third. They're asking us to find dy dx, which notice they're asking to find the derivative of y with respect to x. There's nothing about u in there, is there? And so this is where, I'll show you a different version in a moment, but we can use this right here. We can use this idea that dy dx, you can think of it as the derivative of y with respect to u times the derivative of u with respect to x. And you'll notice the two equations we have. One equation is y equals, and the other equation is u equals. And the idea that, okay, I guess I probably need to address, why does this equal dy dx? Because if we look at dy du times du dx, it's like fractions. The du's can cancel, right? So that's the mathematical reasoning of why it works if you just go back to the basics of what we know about fractions. Now, when we talk about dy du, and maybe I should have done that first. Let me put this up top here. So let's talk right now about what dy du would look like. If y equals u squared plus 4u. So dy du is the derivative of y with respect to u, which in other words, because it's y equals and everything else is in u's, it's just like how we normally take derivatives. Okay, it's just like if that said dy dx and it was y equal and everything was in terms of x's, we just take the derivatives, right? So same thing here. So dy du, the derivative of u squared is 2u, plus the derivative of 4u is 4. So that means dy du is going to be 2u plus 4. While we're here, okay, if this is u equals 5x cubed, when we take the derivative of this equation, we're taking the derivative of u with respect to x. So we take the derivative of that, we're going to be finding du dx, which is the other piece of information we need, isn't it? So what is the derivative of 5x cubed? 15x squared. Okay, so now let's go back to what I was starting to have you guys do. In that, let's plug those pieces in here. We want dy du times du dx. So what is dy du? 2u plus 4. Times, what is du dx? 15x squared. Now, what is it we were trying to find? dy dx. Almost. Why would I say this isn't quite it if we're trying to find dy dx? What do we have in here that doesn't make you think this is a dy dx answer? We have a u in here, don't we? Are we supposed to have a u in here, you think? No. We're not supposed to have a u in there. But what do we know about u? According to our original problem, u is equal to 5x cubed. You see where we're going with this? We're going to substitute that value in. In other words, if you're trying to find dy dx, the idea is it's a y and x thing. We shouldn't have a u in there. Okay, so 2u plus 4, but u is 5x cubed. So 2 times 5x cubed is going to be 10x cubed plus 4 times 15x squared. You could possibly leave your answer like that, or I was going to distribute it. So if I distribute this together, dy dx is going to be what?
It would be 150x plus 25x squared.
I'm with you on 150x to the fifth plus 60x squared. Now, that's kind of the long way. There's times we need the long way, though, which is why I'm showing it. It's trying to understand the pieces, which is what I need you guys to, work to do. On this one, I want to kind of prove to you that this is the correct answer and why it's the correct answer, if you will. It asked us to find dy dx, right? And as we were asked to find dy dx, I'm going to do this over here. It was y equals, instead of working this in terms of u squared. What was u? 5x cubed, quantity squared, plus 4u. 4 times what's u? 5x cubed. Now, I wouldn't take the derivative quite yet. I would clean that up a little bit in that 5x cubed quantity squared is going to be 25x to the sixth plus 20x to the third. Are we okay with what I did?
Oh my goodness.
Is that a good oh my goodness? Okay, you're seeing where I'm going. Okay, so the idea here is that the first time I used the 2 separate equations and made it work. This time, and then I had to substitute in later. This time I'm substituting in at the beginning, and now when we take that derivative, dy dx, what's the derivative of 25x to the sixth? 150x to the fifth plus the derivative of 20x cubed, 60x squared. Hey, guess what? It checks, doesn't it? Okay. I'll be honest. For the purposes of today, I'm going to use more the first one. But I wanted to prove to you why it works based on what we already know, if that makes sense. Questions? Some of you are working on the next one, aren't you? Okay, let's try it then. Let y equal 2 natural log of v, and v equals u squared. Find dy du. I think, I don't know which way you guys want me to do this, but I'm going to start with finding the derivatives of each of these right now. So right here, y equals 2 natural log v. If I find the derivative of that, that is the derivative of y with respect to v. So are you okay if I say that when we take the derivative, that's dy dv? And what is the derivative of 2 natural log of v? Yeah, 2 is 2. Derivative of natural log of v is 1 over v. And so we traditionally write that as 2 over v. Now, what about v equals u squared? Yeah, the derivative of v with respect to u, so dv du. And what is the derivative of u squared? 2u. Okay. Sounds like you guys are okay with that part. Now, we're being asked to find dy du. What are the two derivatives we know here? We were able to find dy dv and dv du. Hey, guess what happens when we multiply those together? My dv's will cancel and I'll get dy du, which is what we want, isn't it? So, have you started filling in? dy dv was 2 over v times dv du, which is 2u. What should I not have in there, though? I shouldn't have a v in there. If we're trying to find dy du, I should not have a v. But that's okay, because what do we know about v? It's u squared, isn't it? So, rewrite. 2 over v is going to be 2 over u squared times 2u. Two over u squared times 2u. 4 over u. I can go with that. Okay. I'm not going to take the time because I don't want to push us any, I don't know, we might be close on time today the way we're already going because we started, late at the beginning, but you could do this the alternate way as well, right? Okay. Example 3. Let y equals sine of t, and t is 1 over the square root of x. What is dy dx? Well, if y equals sine t, what is that when I find the derivative? Derivative of y with respect to t means dy dt, and the derivative of sine t is cosine t. T equals 1 over square root of x. When I find that derivative, I'm going to be doing derivative of t with respect to x, dt dx.
So that's really 1 to the negative. So it'd be negative 1/2 x, which would be negative 3.
Okay, so yeah, if you haven't already, did you guys already think about this? This 1 over square root of x is really x to the negative 1/2, right? Because the square root of x is x to the 1/2. Pull it up out of the denominator, it's x to the negative 1/2. So when we do the derivative of x to the negative 1/2, multiply by the negative 1/2 out front, so negative 1/2 x, negative 1/2 minus 1 is negative 1/2, which is negative 3/2. Or negative 1/2 minus 2/2. I don't know how you guys want to think about it. Okay, we're good with this part? Okay. So what are we trying to find? We're trying to find dy dx. And what are the pieces we know that we hope are going to make dy dx? Yeah, I'm a step behind that, but yeah. We found dy dt and dt dx. Will those make it happen? Yeah, because when you multiply those, the dt's will cancel. Just kind of checking myself here, making sure it's going to happen. So dy dt was cosine t. dt dx is negative 1/2 x to the negative 3/2. Fun stuff there. Which part of this answer am I not supposed to have?
Yeah, it's cosine t when you should have the cosine x.
Yeah, we need dy dx, so we should not have a t, but
But we have to know t is equal to x to the negative.
yeah. T is equal to 1 over square root of x, or x to the negative 1/2. What did I do here? I actually did 1 over square root of x. I'm not sure there's a more, I don't have a difference there of what's more correct. So try that again. So cosine of t, so cosine of 1 over square root of x times negative 1/2 x to the negative 3/2. And I guess if you really wanted to, you could change that into square root form. But honestly, all I did there is I just switched and put the negative 1/2 x to negative 3/2 out front for my final answer is what I did. So I wrote it as dy dx is negative 1/2 x to the negative 3/2 times cosine of 1 over square root of x. Okay. Example B. Yet another definition of derivative. Okay. We already know these two forms. Limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And I think our more preferred form, the limit as h approaches 0 of f of x plus h minus f of x over h. Only because it's easier to write h's than delta x's, right? Okay, so we have a third form of the derivative when given a value x equals a. The limit as x approaches a of f of x minus f of a over x minus a. So again, this is another derivative. How often are we going to use that one? Well, not that often, right? I mean, how often do we use the others now? We don't really. But here's what I'm going to say. Same thing, the whole reason I taught the others. Hopefully you can recognize the others now. When they ask you to take some crazy limit, sometimes when they ask you to take that crazy limit, what they really want you to do is take the derivative.
There was one like that on the AP classroom assignment. It said it was like the big limit, or it did the big limit for definition of derivative. It was like, what is this equal as it approaches this number? and like it wanted you to take it out of the definition and then just plug it into the derivative, which is what I did.
Yep, I'm sure. I didn't say, based on the fact we've done derivatives and definition of derivative, it doesn't surprise me that I had one on there like that. So, which scores were overall better. I glanced at them this morning.
I didn't check it.
So, did it tell you your score right away?
No, it usually
Yeah.
takes a little bit.
Maybe you were the last person to do it. Maybe does it wait then until the last person does it?
I think it's something on your end because.
But see, this time I set it up differently. This time I set it up, I thought I set it up so it would tell you.
That's what Doc does, but it doesn't tell me. So I think it might be
You have
it
to,
might
like-
wait for the last person.
With Docs, you have to like log out and like close the Safari browser, and then log back in, and it will tell you.
Okay, well, I don't know. Scores were definitely better this time. So that was a definite, which we can talk about that sometime.
Last one was so bad.
But last time they were not pretty overall. This time they're much prettier.
Mine were really.
Okay, so next page. Using the alternate definition of derivative to find f prime of a, where f of x equals x squared plus 1, and a is some constant. Now, first of all, because it was on the previous page, first thing I'm going to do is I'm going to write out that definition of derivative. In that, f prime of a is the limit. This time it's as x approaches a of f of x minus f of a all over x minus a. Okay, that is definition of derivative from the previous side. I just need it to be able to point at, to look at, to talk about. I just feel like we do better there. At least I feel like that. Okay, so we're being asked to find f prime of a when a is some constant. So guess what we're going to do here?
Use that.
The limit as x approaches a of f of x. What is f of x? In our particular problem, x squared plus 1 minus, what is f of a?
A squared.
Yeah. If f of x, side note here, if f of x is x squared plus 1, every place I see an x, I replace it with a, and so f of a is a squared plus 1. Have we gotten over that big hump of, that was an issue at the beginning of the year. So now when I subtract this, notice I'm going to put it in parentheses. It is minus a squared plus 1, which ultimately really means it'll be minus a squared and minus 1 over x minus a, which is x minus a. Okay, let's do some cleanup. Good mathematical habits is that I rewrite the limit as x approaches a. Create those good habits now, folks. How does my numerator clean up? Do the ones cancel? X squared stays x squared. We have a minus a squared, and it ends up being 1 minus 1. Okay? Over the denominator, x minus a. Do we see the next step?
So is x minus a, is that the same thing as quantity x minus a squared? Like x squared minus a squared, would that be the same as like having in parentheses x minus a squared?
It is not.
Do we multiply by the quadrant or something?
I would not.
Is it really easy?
Do we just
Cancel.
plug in a for x?
No, we can't cancel, okay? Because it's x squared minus a squared and x minus a, those are not the same. I cannot cancel. And like I can't cancel just an x or just an a because they're being subtracted. Let me do a what if here. what if that numerator was x squared minus 25?
Factors into x plus 5, x.
Factors into x plus 5 and x minus 5?
Mm-hmm.
So x squared minus a squared factors into x plus a and x minus a. In other words, it is the difference of squares is the vocabulary there. Sound familiar? From your Algebra 1 days, technically, but Algebra 2 days more recently. Now, why did I want to factor that? Now we can talk canceling, because now we have a factor of x minus a that cancels with another factor of x minus a. So, cleaning up, I now have the limit as x approaches a of x plus a is all I have left. How do we actually take the limit? We plug a in for x. And so instead of x plus a, we're going to say a plus a. And what is a plus a? 2a. Does it make sense, folks? Think about what you know about derivative. Our original function was 2x squared plus 1. What's the derivative of x squared plus 1? 2x. When x equals a, it's going to be 2a. We did it the long way, right? Which we have to practice at. Okay. This is, you saw in AP Classroom, if Ross is right in what he's saying there, they threw a definition of derivative at you and said take the limit. Okay. That's, you know, the kind of stuff they'll do. Could they do it with this scenario? They could. Okay. Okay, moving along then. Example 5. Let f of x equal x squared. Use the alternate form of the derivative to find f prime of 1. So what is that saying this time? Yeah. So 1 is going to be our what value? That is our a value, yes? Okay, so we're still using that same definition of derivative from last time. I'm not going to rewrite it this time. I'm just going to draw a big arrow. So this time we're being asked to find f prime of 1. So this time it's supposed to be the limit as x approaches a. Well, what did I just talk about? The fact that a is 1. So anytime our definition says a, we're actually going to put in a 1. So we're doing the limit as x approaches 1 of f of x, which is x squared, minus f of a. But f of a is really f of 1. And what's f of 1? I mean, if you want me to be technical, I can write 1 squared. But we all realize 1 squared is 1. Over x minus a. What is a? X minus 1. So, I don't know if you need it. What we did right there is we did f of x minus f of 1 over x minus 1. I probably should have written that step out first, now that I think about it. What do you see? Yeah. Just like the previous problem, we can factor it, right? X squared minus 1 is difference of squares. So it factors into x plus 1, x minus 1, all over x minus 1, and a factor of x minus 1 cancels with a factor of x minus 1, and we are left with the limit as x approaches 1 of x plus 1. How do I take that limit? Plug in 1 for x. We get a very difficult math problem here. 1 plus 1. Oof. Might need some remedial math
I'm
here.
just gonna shout out some.
I was waiting for someone to give me some random answer other than
2
2.
square root of 8.
Oh, he's gonna get fancy here.
Like I was trying to think of like one that was like so like complex.
Okay.
Third root.
Can you kind of check yourself here, guys? What's the derivative of x squared?
2x.
2x. Evaluated at 1? 2 times 1 is 2. Or Maddie may say 4, and Ross may say 2 squared. I don't know, but I'm going to go with the basics here. Okay, moving along. Okay. Example 6. F of x is the fun cube root of x. Use the alternate form of the derivative to find f prime of negative 1. Which, what is that negative 1 then?
A.
That is a. Okay, so I'm not going to recopy definition derivative on this page. You guys have it at this point. You can look up. We want f prime of negative 1. So what kind of limit am I doing here? Okay, the limit as x approaches negative 1. F of x I'll go ahead and leave it as cube root of x for a moment. Minus f of negative 1.
So it'd be plus.
Negative 1.
Okay, so for the brief moment, I'm going to say the cube root of negative 1 to not lose anything in confusion here. Obviously, we're going to clean that up in a moment. Over the denominator of x minus a, which is negative 1. So yes, I just wrote that as x minus negative 1. But as I said, I'm going for a cleanup step. The limit as x approaches negative 1. First of all, if I recall, we're going to talk powers here. Yep. So instead of cube root of x, how else can I write that? X to the 1/3 minus, what is the cube root of negative 1? Negative 1, yes? So minus a negative 1 is really plus 1. And over x minus negative 1, which is x plus 1. Okay. Now, what happens if we go ahead and plug negative 1 in right now?
You'll get 0 over 0.
You'll get 0 over 0. And so we haven't finished yet.
Am I right in saying that you could somehow like factor out a third root of top?
It's not that we're going to factor out a third root, but what we're going to do is we're going to set this up so that these are, which way? So the denominator is the sum of cubes. And we're going to factor like that. So I'm going to rewrite this. I always have to stop and think about how this one works. So, okay. The limit as x approaches negative 1. On top, I'm going to leave it as x to the 1/3 plus 1. Now, the denominator, I'm going to get fancy with. Instead of just calling that a plain old x, that's too boring for this problem. Okay? X, how could I rewrite x using an x to the 1/3? In other words, x to the 1/3 raised to the 3rd is equivalent to saying x. And yes, there's a reason for my madness. This is the challenge level. Okay? Now, what we have happening here, I just set that denominator up as the sum of cubes. And this is that factoring. We've done it a couple of times. We're going to practice it again here. So limit as x approaches -1. My numerator stays as x to the 1/3 plus 1. And we use the f and the s's here.
I think I remember something like that.
I think that's what I've used. That's what I've written here. So what we're trying to do is we're trying to factor f cubed plus s cubed, where they're both perfect cubes. And so when we factor that, we factor into a binomial that is not f plus 3. It's f plus s, where those are the binomials, the cube root of each of the terms. And then the trinomial is f squared minus fs plus s squared. So that's your reminder of the form. Now, of course, we're going to do this with a challenging problem on top of it. Okay? So, x to the 1/3 cubed. Good news, we can already see it. What's the cube root? I mean, originally it was x. What's the cube root of x? Cube root of x is the cube root of x, right? Or, right here it is x to the 1/3. So we're going to have x to the 1/3. Because my original problem is plus, we keep the plus in the binomial. What's the cube root of 1? 1. So that's my binomial. We took the cube root of each of these pieces. I wonder why we're doing this, right? Now, we've still got to get the trinomial right to make this happen, though. So now, when it says f squared, I'm taking my first cube root, which was x to the 1/3, and I'm squaring it. What is x to the 1/3 squared? X to the 2/3. This sign is always opposite, so it's going to be minus. And this is the two terms from the binomial multiplied. So it's the two cube roots, so the x to the 1/3 times 1, which is just 1x to the 1/3, or in other words, x to the 1/3. It's always plus s squared, you're always adding. And this time we square the other cube root, which our other cube root was 1. 1 squared is 1. As it was already pointed out, there was a reason, right? What happened along the way? Yeah, x to the 1/3 plus 1 cancels. So officially our limit at this point is the limit as x approaches -1 of 1 over x to the 2/3 minus x to the 1/3 plus 1. And now to finish this problem off, we take the limit, which means we're going to plug in -1. 1 stays my numerator. Sorry, I confused myself. Now I'm plugging in -1. So -1 to the 2/3. So I'm going to say what's the cube root of -1, which is -1 squared, which makes it +1. Okay, minus x to the 1/3. So what's the cube root of -1? -1. And then +1. Does that make sense what I did there? So 1 over 3. Okay. That was a challenge just because of the 1/3, but it got us to review sum and difference of cubes. So, okay, one more. And that is the symmetric derivative. So we're really learning two new definitions of derivative, really. We had the front one, which I think, do they just call it alternate definition? which is the f of x minus f of a over x minus a. And then we have the symmetric derivative. And the symmetric derivative, the limit as h approaches 0 of f of x plus h minus f of x minus h all over 2h. And guess what? We have to use the symmetric derivative. So we ready to try it? As ready as it gets, right? Good news is we should be able to make it out of class on time. Okay, so we're being asked to find f prime of x. And we're using that definition of derivative, right? Definition of derivative is the limit as h approaches 0 of. Okay, how do you feel about this, guys? If, okay, I'm going to do a side note over here. If f of x is x squared plus 15, we sometimes still struggle with this. So what is f of x plus h?
X plus h plus h squared plus 15.
Yeah. You take that x, and we're going to replace it with an x plus h. So x plus h, quantity squared, plus 15. And I would, for the first step, write it like that until we see what's going on and what it looks like and decide if we have to go farther, which we might have to go farther, but I'm not ready to go there. So this is x plus h, quantity squared, plus 15, minus f of x minus h. I don't need to write that out over here, do I? So now I'm going to put the whole thing in parentheses. And then just instead of saying x plus h squared, I'm going to say x minus h squared plus 15. So I really have two sets of parentheses happening there. All over 2h. Okay, guys. We're going to have to do some multiplying out. I had a feeling we would, but limit as h approaches 0. Okay, what do you know about x plus h, quantity squared?
X squared plus 2hx plus h squared, right?
I can go with that. X times x is x squared, right? X times h is xh or hx, and then another one is going to be two of them, right? Plus h squared. What do we have to carry down from above? Plus 15. Don't overlook that. Now, I don't know, how talented do you guys feel? Because what do we have to do? We have to subtract everything in the next parentheses. Can we go ahead and change those signs as we go? Okay, so when we square x minus h squared, it would be x squared, so I'm going to say minus x squared. It would be minus 2hx, so I'm going to say plus 2hx. It would be plus h squared, so I'm going to say minus h squared. It is plus 15, so I'm going to say minus 15. All over 2h. Is there magic happening here?
There's cancellation.
That's magic, right? No? X squared minus x squared. H squared minus h squared. 15 minus 15. That's magic. You don't like me calling that magic?
And
It's math. Yep, I was going to do that in the next step here. So limit as h approach 0, 2hx plus 2hx is 4hx over 2h. I don't know, some of you guys just you go ahead and cancel it right there, but in technicality, it should wait to cancel right here. But yes, we have an h on top and an h on bottom, which is good, because otherwise we're stuck. We need those h's to cancel. I just canceled the wrong thing, though. Well, h and h canceled, which, what else could you do there? 4 over 2 is going to become 2. So really what we have here, the limit as h approaches 0 of 2x. What is the limit as h approaches 0 of 2x?
Oh, it's just adding 2x.
2x, right? Because we don't have any h's to plug in for. So it is just 2x. Go back up and check yourself. Is 2x the right answer?
Yes.
Yes, the derivative of x squared plus 15 is 2x.
So we're gonna have,
We really can't be talking at the beginning of class, but I wasn't ready to go today either, so.
we're gonna have 3
Okay.
homeworks